Then rearrange it to let u plus uk plus 1 on the left hand side and leave everything else on the right. T, K, A, B are fixed, so we will get a form of recursion. This is coefficients. Because the coefficients of the difference equation changes with t, so the sample rate is fixed to make sure t is constant. A control design problem. We construct a controller in a continuous time and fix the control gains with reference to figure 2. Figure 2, where is that? Okay, anyways. Okay, this one. Let me cut it and paste it over there. So use inverse Laplace transform to obtain a differential equation using ET input ET and output UT signal of the controller. So ET is here, UT is here. And use Euler approximation to approximate derivatives with difference. And remember S equals d dt. Express UT as a function of ET, which we did before. Consider DAC conversion. DAC is digital analog converter, followed by a ZOH, zero order holder. Here it says the control scheme depends on the sampling frequency 1 over t. If t is small enough, then the approximate error introduced due to the use of the OH is small, thus to an acceptable control performance. And he says, for this to be the case, the sampling rate has to be much greater than the one suggested by Nyquist's sampling theorem. And he illustrates the example below. So to illustrate the effect of a sampling interval t on a control performance, we apply the controller of the previous subsection k equals 70 a b to a plant with transfer function g. First, consider step response for a closed-loop system with a continuous controller. Comparing with HLT 160, let me check and draw the graph on our videos. 168. 168, so this gives us a graph. Let me take a picture. Can I take a picture? I don't know if I can take a picture when I record things. So basically it's if I add more, so this is the step response, and the y-axis is amplitude, and the z-axis is time, or it can step response with continuous controller. Let me delete this graph to make it clean. It looks like a second order response with omega equals 2 pi f0 equals 1 and the damping coefficient to be 0.4. So these are from the graph we are given. It will have the annotate the graph with the different damping coefficients. We see the response is dominated by these poles. Dominant poles, it's good to revise the control system to understand these concepts. Euler approximation would be adequate when t interval is small enough, but less good when t is large. These sentences are important because in exam we will sometimes be asked what is your assumption when you use this approximation. Figure 13 shows the step response when sample rate is 80, cell 40, 20. So he's choosing a different t and to compare. The description between the continuous system and the discrete approximation. So this is our true system and discrete is our approximation. So when the sample rate reduces, which means t is increasing. So when sample rate reduces, you see the discrepancy is becoming greater. According to Nyquist theorem, the sample frequency should be at least twice the bandwidth of interest, but it should be clear from the preceding example that we must sample at much higher rate when use the Euler approximation. So these are also important assumptions we want to make, like conditions to use. So here we give a approximation that we want to use the Euler approximation. We need to let the frequency bigger than 30 times the bandwidth system. I had this